Hello everyone, welcome to Basic Electronics Tutorials. In this video, I am going to discuss on the common emitter configuration of a BJT. I will be discussing on the mathematical analysis, input and output characteristics of the common emitter configuration by considering an NPN transistor in this video. So, let us start with it. Before we start on the discussion of the common emitter configuration, I highly suggest you to watch my previous video on punch through effect in a BJT. That video will be a prerequisite for this video and you can watch the same by clicking on the link shown in the top right corner right now, or I will leave the link of the same in the video description below. Coming to this video's topic, consider the NPN transistor in the common emitter configuration as shown in figure 1 here. The input signal here is applied between the input terminals, which are base and emitter, and the output is taken from the output terminals, which are collector and emitter. We use two signal sources here. The input signal source is called VBB, the output signal source is called VCC. As you can see, the input signal VBB is connected across the base and emitter terminals, and the voltage across these terminals will be represented by VBE. Coming to the other voltage source, which is VCC, it is applied across collector and emitter terminals, and the voltage across these terminals be denoted by VCE. Let us now recall the equation that relates the currents in a BJT, which is given by emitter current IE equal to base current IB plus the collector current IC. In the common emitter configuration, the input current is the base current and the output current is the collector current. By analyzing the equation for the current in the BJT, which let me call is equation 1, we find that for the common emitter configuration, the output current, which is IC, is greater than the input current, which is IB. Therefore, we can now say that the common emitter configuration has a current gain parameter beta equal to the ratio of IC divided by IB, and since IC is greater than IB, this will be greater than 1. The typical values of beta ranges between 20 and 200. Let us now talk about the voltage gain for the common emitter configuration. The voltage gain parameter is AV and it is simply the ratio of the output voltage divided by the input voltage. Output voltage can be written as the product of the output current IC multiplied by the output resistance RC, and the input voltage can be written as the product of input current IB multiplied by the input resistance RB. Let me now split this into IC divided by IB multiplied by RC divided by RB. You should note that the common emitter configuration has a high input impedance and low output impedance. So, the value of RC will be low compared to the value of RB, because of which the ratio RC by RB here will be less than 1. However, as already said, the ratio of IC by IB, which is the current gain parameter, is greater than 1, and therefore, for common emitter configuration, the value of voltage gain will be greater than 1. Another very important thing you must note about the common emitter configuration is that this is a inverting amplifier circuit. This indicates that the output signal has a 180-degree phase shift with respect to the input signal. Let me now discuss the mathematical analysis for the common emitter configuration circuit. Let us start the mathematical analysis by applying the Kirchhoff's voltage law to the input loop, which involves VBB, RB and voltage across the base to emitter loop. By applying KVL to the base to emitter loop, the resulting equation would be VBB minus of VBE minus of IB into RB equal to 0. If I rewrite this equation for the base current IB, I will obtain the expression as VBB minus of VBE divided by RB. In a very similar fashion, let us now apply KVL to the output loop, which is across the collector and emitter, and let the voltage across the collector and emitter be represented by VCE. When I apply KVL to the collector emitter loop, the resulting equation would be VCC minus of VCE minus of ICRC equal to 0. If I now rewrite the expression for IC, it would be IC equal to VCC minus of VCE divided by RC. Another very important equation for the common emitter configuration is that the value of the collector current IC is equal to beta times the value of the input current IB. Please note, we will be using these equations to understand the input and output characteristics for the common emitter configuration circuit. Let us now start the discussion on the input characteristics first. First of all, let us understand how to obtain input characteristic curves. Input characteristic curves can be obtained by plotting the voltage across the input terminals, which is VBE, and recording the input current, which is IB, at a fixed value of the voltage across the output terminals, which is VCE. So, for the input characteristic curves, the x-axis will be the voltage across the input terminals, which is VBE. Y-axis will be the input current, which is IB. And we need to now record these values for a fixed value of voltage across the output terminals, which is VCE. Let us start the analysis. Consider the voltages with polarities as shown across both the input as well as output. Assume that the output signal VCC is positive and is greater than 1 volt. Coming back to the input voltage, let us now assume that the voltage across the input terminals VBE is greater than or equal to the threshold voltage required to break the base to emitter junction. When this happens, the base current IB starts to rise in an exponential fashion. This is indicated in the common emitter input characteristic curve with the first characteristic curve, which is towards the left. As previously said, input current IB is positive, the input voltage VBE is also positive, and therefore, we will obtain the input characteristics in the first quadrant. Please note, VTH here represents the minimum voltage required to break the base to emitter junction and forward bias that junction so that the input current IB starts to flow. Let us now understand what will happen to the characteristic curve if I now increase the voltage across the output terminals, which is VCE. Please note, I have already discussed about the punch through effect in my previous video, and I hope you already have referred to that video because I will be referencing that effect for understanding both the input and output characteristics for common emitter configuration. Let us now assume that I increase the value of the collector to emitter voltage. Please note, we have considered an NPN transistor. When the collector to emitter voltage is increased, the collector is now at positive potential and emitter is at negative potential. Coming to the base terminal, please note, we have connected positive terminal of VBB to base terminal. So, base is also at positive potential now. To understand whether the collector to base junction is currently forward biased or reverse biased, we need to now analyze the potential difference between the collector and base terminals. Let us assume that the voltage VCE is greater than the voltage VBE. So, the potential difference across the collector to base terminals, which is VCB, will be greater than 0. This means now the collector is at a higher potential and the base is at a lower potential. Therefore, the collector to base junction will be reverse biased. Under this condition, any increase in the collector to emitter voltage will cause early effect, which causes the depletion region width between the collector and base region to increase, causing the effective width of the base region to decrease. Let us recall the equation that relates the current in a BJT, which is IE equal to IB plus IC. Since increasing the value of the collector to emitter voltage decreases the base region, the effective base current will decrease. You should note that since the collector to base junction is reverse biased, the collector current is effectively constant, and therefore, to compensate the decrease in the base current, the emitter current must also decrease. When I say the emitter current decreases, you should note that it is a rate of change of the input current that changes. Since it is decreasing, the slope of the input characteristic curve will decrease. Coming to the input characteristic curves, please note I have shown the input characteristic curve graphs for three different values of the collector to emitter voltage, where VCE1 was the smallest. If I increase the value of VCE, what happens? The slope of the characteristic curve decreases, and therefore the rate of change of input current decreases, and this causes the characteristic curve to shift right. If I further increase the collector to emitter voltage to, let us say, VCE3, the characteristic curve will shift further towards the right. This is the impact of variation of voltage across the output terminals on the input current for the common emitter configuration circuit. Let us now continue the discussion to the output characteristics. Let us first understand how to obtain the output characteristics for the common emitter configuration circuit. Output characteristics can be obtained by plotting the voltage across the output terminals, which is VCE, and recording the output current IC at a fixed value of input current IB. So, for the output characteristic curves, the x-axis will be the voltage across the output terminals, which is VCE. Y-axis will be the output current, which is IC, and these values are to be recorded for a fixed value of input current IB. Before I move on to the analysis of the output characteristics, I would like to discuss about the different regions of operations in a BJT. Please note, I have already discussed about the region of operation in my previous video on BJT construction as well as BJT configurations. I will leave the link of those videos in the video description below, and you can watch them at your convenience. Let us consider the table that is shown here. In this table, the leftmost column represents the state of the base to emitter junction. The second to left column represents the state of the collector to base junction. The third column from the left represents the region of operation, and the last column represents the application for the corresponding region of operation. As previously discussed, the output characteristic curves of a BJT has three different regions of operation, and the region of operation depends upon the state of the base to emitter junction and the collector to base junction. Let us consider the second row as what is shown here. If the base to emitter junction is reverse biased and the collector to base junction is also reverse biased, then the BJT operates in the cutoff region of operation, where it is said to be officially in off state. Since the BJT is assumed to be in the off state, there are no applications for this region of operation. Let us consider the next row now. When the base to emitter junction is forward biased, but the collector to base junction is reverse biased, the BJT operates in the active region, where it is used as an amplifier. Coming to the last row, when both the base to emitter junction as well as the collector to base junction are forward biased, the BJT operates in the saturation region, where it is used as a switch. Let us now analyze the common emitter configuration circuit for these three regions of operation. Let us start the discussion by denoting the voltage across the base to emitter as, let us say, VBE. Since there are three regions of operations in the output characteristic curve, I will be considering three different conditions for either forward biasing or reverse biasing the respective junctions. Let us start from the input loop first, which is across the base and emitter. Assume that the voltage across the base and emitter terminals is less than the voltage required to break the base to emitter junction. For such a scenario, the base to emitter junction will be reverse biased and the base current will be 0. Coming to the output loop, that is between collector and emitter, let us assume VCC is positive and is equal to 10 volt. Under this condition, the collector will be at plus 10 volt potential and emitter will be at minus 10 volt potential. Coming to the input loop, since we have assumed the base to emitter junction voltage is less than the threshold voltage, the base terminal will be at a potential less than or 0.7 volt, assuming the transistor is made up of silicon. So, if you now look at the potential difference between the collector and base terminals, it would be 10 minus of 0.7, which will be 9.3 volts. That is, you are effectively applying plus 9.3 volts to the collector, which is made up of N semiconductor region, and applying minus 9.3 volts to the base, which is made up of P type of semiconductor region. Since now the collector is at a higher potential than at the base, the collector to base junction is reverse biased. So, currently the base to emitter junction is reverse biased, the collector to base region is also reverse biased, and therefore, the device is now said to be operated in the cutoff region. Let us recall the equation that relates IC and IB for this, where IC equal to beta IB. Now, since the base to emitter junction is reverse biased, base current being 0, the collector current will also be 0. Please note, this is only under idealistic scenario. In practical transistors, there will be a small leakage current flowing across the device even when both the junctions are reverse biased. The characteristic curve that we obtain under this condition is said to be the cutoff region of operation. Coming to the characteristic curve itself, please note, currently the base current is 0. The curve for the collector current for the condition when IB equal to 0 represents the cutoff region. The region of the characteristic curve for the collector current line for IB equal to 0 is called the cutoff region of operation. It should be noted that in this region of operation, the transistor is effectively in off state. Let me now consider the second region of operation, which is active region of operation. Once again, starting from the input supply voltage, let us assume that the voltage across the base to emitter terminals is equal to the threshold voltage required to forward bias the junction. So, the base to emitter junction is now forward biased. You must note that for this exact case, the voltage across the base terminal will be equal to 0.7 volt. Coming to the output loop, let us retain the same 10 volt applied across the collector and the emitter terminals. As previously discussed, this will cause the collector to be at plus 10 volt potential and emitter to be at minus 10 volt potential. Coming to the collector and base junctions, since the collector is at plus 10 volt and base is at plus 0.7 volt, the potential difference between the collector and base terminals will be positive, and therefore, the collector to base junction is once again reverse biased. You should now note that the base to emitter junction is forward biased, but the collector to base junction is reverse biased. For this condition, the transistor enters active region of operation. Let us now once again quickly recall the collector current equation, which is given by let me also write another equation that relates the current in a BJT, which is given by IE equals IB plus IC. Please note, currently the collector to base junction is reverse biased, and now any increase in the voltage across the VCC will make the depletion region width between collector and base region to increase, which will cause the effective base width to decrease. When the base region decreases, as already discussed, the base current decreases. If you look at this equation carefully, you note that for this condition, the input current IE is fixed because VB is fixed, IB is being decreased, and in order to compensate the equation, the value of IC has to increase. Therefore, in the common emitter configuration circuit, as the value of the collector to emitter voltage is increased, the collector current increases, but the increase is not sharp but a very slow increase. This is shown in the characteristic graphs here. Let us consider IB1 here, and you can see the characteristic graph has a finite slope, but the slope is very small. So, we understand that for the common emitter configuration, increasing the voltage across the collector to emitter terminals increases the collector current in a very small order, and therefore, the characteristic curve has a slope. Coming back to the discussion, please note we have now discussed the characteristic curves for a fixed value of input current IB. Let us now discuss what will happen if the value of IB is increased. The answer for that is pretty simple. Recall the equation that relates the output and input currents for common emitter configuration. We know that IC is equal to beta IB. So, now if I increase the value of IB, as per this relation, the collector current should also increase. Therefore, if I now consider a higher value of the base current, which let us say is IB2, the collector current increases by a value of beta. Please note, beta value is fixed for a transistor. If I continue performing this operation, then you can see an increase in the collector current every single time the base current is increased. Please note the relation between different base currents I have used in this graph. Let me now discuss on the last region of operation for the output characteristic curves, which is the saturation region of operation. Let us assume that the voltage across the base to emitter terminals is now greater than or equal to the threshold voltage required to forward bias the base to emitter junction. Assume this value is equal to, let us say, 2 volt. Since the base to emitter voltage is positive, the base to emitter junction will be forward biased. Let us now talk about the output voltage now. Let the output voltage VCC be very small. When I say small, I will assume this to be around 0.2 or 0.3 volt. These are the effective values. Let me demonstrate the operation for 0.2 volt across the VCC. So, the collector is now at plus 0.2 volt potential and the emitter is at minus 0.2 volt potential. Coming to the base to emitter region, since I assume the value of VBE as 2 volt, the base is at plus 2 volt potential and the emitter is now at minus 2 volt potential. If I now compare the potentials across the collector and emitter, the collector is at 0.2 volt potential and the emitter is at plus 2 volt potential. So, the effective potential difference between the collector and emitter is now minus 1.8 volt. This means that you are now applying a negative voltage to the collector, which is the N type of semiconductor material, and the base is at a positive potential of plus 1.8 volt. This will forward bias the collector to base junction as well. And when this happens, since the base to emitter junction is already forward biased, the transistor enters the saturation region of operation. Let me recall the equation for collector current very quickly now. IC is equals to VCC minus of VCE divided by RC. Since now both the collector to base junction and the base to emitter junctions are forward biased, the value of the collector to emitter voltage drops rapidly. This rapid decrease in the voltage across the output terminals will cause the collector current to rise rapidly since they are inversely proportional to each other. This is shown in the common emitter characteristic curve in this region of operation, where you can see the collector current is shown to rise rapidly. The region of the characteristic curve where the collector current rises rapidly is said to be the saturation region of operation, and under saturation region, both the collector to base junction as well as the base to emitter junction are forward biased. Once again, since IC and IB are related by the equation IC equals to beta IB, any increase in the base current will create a rapid increase in the collector current as well. Because of this, you can see that the slope of these characteristic curves in the saturation region depends upon the value of IB. Higher the value of IB, higher will be the slope. Well, with that, we have now completed the discussion on the output characteristics of a BJT in the common emitter configuration. And we have also discussed the conditions for the different regions of operation in the output characteristic curve. It should be noted that I considered an NPN transistor for this discussion. If you are asked to discuss the common emitter configuration for a PNP transistor, the only change would be the reversal of polarities of all the voltages and currents in the configuration circuit. Well, with that, we have come to the end of this discussion on the common emitter configuration. In my next video, I'll discuss the common base configuration circuit. So, stay tuned. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.